everyone, welcome back to the channel. It's the Caribbean Bookworm, and first and foremost, if you're watching this video throughout the holiday season, I wish you happy holidays and I hope all goes well with you in the start of this new year 2024. Now, to start off the topic of our video, the topic of this video is about a particular conference which is in the very similar spirit as to the Solvay conference, which a lot of people may have heard of or may have seen this very famous picture of. And the picture that you're seeing right now is of the Solvay conference in 1927. It's the picture, as you could have seen, that has so many famous scientists like Einstein, Marie Curie, Bohr, Heisenberg, Paul Dirac, so many people which I can't even name all of them at the moment. And it was a conference held in Brussels where a lot of physicists came together, and the topic of that year was on electrons and photons. And in particular, it was the conference which made physicists have major breakthroughs afterwards when it came to quantum theory. So it allowed them to unravel some of the mysteries of quantum mechanics at the time as it was being developed, especially very intensely around those times, and they were able to interpret what this new theory actually meant. So that's where you had famous discussions such as the discussion between Bohr and Einstein about God not playing dice and whether or not nature is deterministic or probabilistic. At the end of the day, the probabilistic interpretation is what a lot of people went with and is what we still use for the most part when talking about quantum mechanics. But lo and behold, there was a very similar type of conference, but perhaps not as well known when it came to things that inspired later deeper theories in quantum mechanics, namely quantum field theory. And that is the so-called Shelter Island Conference. This was a conference held in 1948. It was a conference that took place at Ram's Hat Inn, and it involved some very well-known scientists, but particularly, especially scientists that you may have heard their names, especially due to their involvements corresponding with the Manhattan Project, such as J. Robert Oppenheimer, most notably, but you also had Hans Bethe, Weizsäcker, and you had a lot of also new up-and-coming physicists, such as Julian Schwinger, Richard Feynman, and many other younger names that also participated in the conference. But I mentioned some of the most notable ones, which I remember off of the top of my head, since there were quite a few people, but not as much as the Solvay conference. So the nature of the Shelter Island Conference, or the topic of it, so to say, like the Solvay conference was on electrons and photons, the Shelter Island Conference was on the fundamentals or foundations of quantum mechanics. And it was pushed forward primarily for a networking opportunity for theoreticians, especially after World War II, and B, was also pushed to discuss some new experimental findings which seemed to hint at very interesting things when it came to quantum electrodynamics, the quantum nature of how matter, charged matter, interacts with the electromagnetic field. And those two experiments were, for one, the lamp shift, which, if you've seen my video on Oppenheimer, you've heard me talk a little bit about the lamp shift. But to summarize, when one looks at the hydrogen spectrum, especially in the context of spectroscopy, so when you have just a proton and an electron kind of orbiting it or just being in a bound state of the thing, the electron can be at various energy levels, at various excited states. However, each energy level, which one would denote with something called the principal quantum number. So each overarching energy level, or Bohr shell, consists out of also these smaller subshells. So these smaller energy levels which you can have as that one primary or one principal quantum number can split basically into various smaller energy levels. So if you have an electron basically in one energy level, say n equals 2, it cannot only be in n equals 2, but it can also be in these various things called subshells. And if the electron in the hydrogen atom was excited for a reason or another, and it slowly loses energy and drops, it emits a light of a particular wavelength. And this can be measured by experimentalists, particularly people doing stuff with spectroscopy. And a lamp, alongside with Rutherford, in a particular experiment, studied the various microwave emissions from hydrogen gases and noticed that there were some findings which seemed to align perfectly with there being a particular energy difference on the second energy level. And this alluded to something related to quantum electrodynamic effects. But we shall jump into those when talking about the content of the conference. So that experiment was one that was particularly interesting, and another one was the so-called Conversi experiment, which I probably butchered the name. It was an Italian name, if I'm not mistaken, but it was an experiment with cosmic rays, which were particularly interesting back then, and I honestly think should be of also particular interest right now, especially in an era at which we build so many large colliders, but they're getting more and more expensive. Cosmic rays are a natural way of studying how particle scattering happens. You get these many exotic particle interactions happening, and you get them practically for free as we're constantly bombarded with radiation from the universe, from various cosmic sources. So, what they used to do a lot in the early days, in the 20s going onwards, was they used to have these balloons, as you would have, for example, in a nice summer evening, like a nice romantic balloon, but they place detectors in them instead of like young couples, and you have them going upwards at very high altitudes. And these detectors would be things like cloud chambers and things like that, which would record various tracks of like particles that are passing through them as you have this radiation like up there as the atmosphere gets thinner. And they would compare basically what you'd measure with the amount of radiation tracks. I'll show you in an image for more clarity, compared to what you'd observe on the ground, on the earth, basically. And this is how a lot of new particles were discovered back then. This is how people came to know that there were much more than just protons and electrons out there, but so many other particles with so many other exotic names and other exotic properties, actually. So these two things were things which inspired this Shelter Island conference. But to explain that latter and also the former experiment a little bit more in depth, I will actually delve into the content of this 3-day conference which happened, and I will try to summarize it as brief as I can, but also in the most interesting manner as I can. So the first day basically was the day which all of the, or a lot of the experimental findings were brought to the table. So the first presentation was given by Lamp, so D. Lamp, who discovered the lamp shift, and he presented his findings basically to the scientists, and they discussed basically the numbers and numerical values which were obtained, as especially it had to do with, if you know a thing or two about orbitals, you know that there are s and p orbitals, and you have at various principal quantum numbers various types of orbitals being encapsulated in that principal quantum number. At the second quantum number, so at n equals 2, there are both p orbitals, so 2p orbitals, and also 2s orbital in there. And what Lamp noticed was a light emitted by an apparent energy difference between the 2s orbital and the 2p orbital. More specifically, 2s half minus 2p half, but details aside. This measured energy difference, which corresponded with 0.03 like inverse centimeters, plus minus some error like estimate, needed clarification, as originally experiments had been done to show that you can have the splitting effect of the energy levels of hydrogen atom with things like a magnetic field being present, like the Zeeman effect, either strong or weak Zeeman effect. But in this case, it wasn't with magnetic fields. In this case, it was just a very fine, precise thing that was being measured. And the main thing which was suggested to have caused this very small energy difference, but relevant because it's being measured, was a suggestion that was primarily made in the conference by Oppenheimer. And his thought, or his hunch at least, was that this perceived energy difference that is being measured could be caused by quantum electrodynamic effects. So as you have the electron be in this like higher energy, like sub shell, you could say, because in quantum electrodynamics you can have that the vacuum around something itself has a non-zero energy. It's something called the 0 point energy. It's a very bizarre concept, but basically you can have that even if I have a finite volume which is completely empty, completely just vacuum, you can have particles popping in and out of existence, which sounds a lot like fantasy, but it is something which its effects can be measured, as long as basically this popping in and out of existence is not basically done in a very long span of time. So it's done in a very, very ridiculously short span of time. this has to do with the Heisenberg uncertainty principle, but it sounds very woo-woo, so perhaps it will make sense as we continue to go along, because this is a very weird and bizarre concept and I probably won't convince you immediately of it. But the thought was that because, at least according to some theoretical frameworks that were being made, that this popping in and out of existence of various ambient particles around the electron could cause it to get a nudge, basically, to kind of drop into a lower energy level. So it could perturb the system and cause this perceived lamp shift. And this hunch was not immediately accepted because, of course, this theory of quantum electrodynamics was not properly well known, and it had a lot of gaps, so to say, that were still needed to be refined. So this hunch of Oppenheimer's was left as a hunch, at least for the first day, but Weizsäcker, which was one of the other theoreticians there, continued to think about the idea and came on, like, added onto it afterwards. So the second presentation was on, in the morning session at least, was also on an experiment, but in this time it was from Isidore Rabi. And Rabi also presented on some of the experimental findings that he obtained along with his colleagues on the hyperfine structure of the hydrogen. So both Lamb and Rabi talked about experimental findings on the hydrogen atom. I can't discuss much about Rabi's work beyond some observations with the frequency of light being observed from deuterium and hydrogen differing greatly from some of the theoretical calculations. I cannot touch upon it much more than that because I didn't properly understand everything which was the gist of that. But it was a very interesting read, but it didn't tie as nicely into the narrative as the following talk, which was given in the afternoon by Rossi, another physicist, on the converticy experiment, which I alluded to earlier. And that was that the meson particles, which were being detected by cosmic ray detectors in balloons, basically, in high altitudes. And this converticy experiment alluding to the fact that there were huge amounts of meson produced apparently in the high altitudes, as was measured with their cloud chambers and like their particle detectors basically that they had back then. But at sea level, that wasn't the case. At sea level, the amount of mesons that were apparently measured from things like carbon isotopes were not as prevalent, you could say, as it was in high altitudes. And an explanation needed to be warranted for this intense discrepancy. So that was the thing which Rossi presented with his talk on the converticy experiment. And later, basically in the evening, there were basically two talks, one of them being on Oppenheimer and him talking about some of the prospects of doing cosmic ray detection in even higher altitudes, like with rockets and things like that. And then later Hans Bethe talking about his work with Richard Feynman, like his student back then, on basically the interpretations of these various cosmic rays experiments. Then entered the second day, at which you had immediately in the morning, starting off with Kramers. Kramers is also a name that is quite often associated with a lot of things in physics, especially quantum mechanics. And he had this theory, basically, he wanted to tackle the issue of quantum electrodynamics, and namely the issue that, in quantum electrodynamics, from the past, even, there seemed to be this problem of renormalizability. And that's a mouthful, but that basically says that if you were to compute the energy difference that one would obtain if quantum electrodynamics were to be a thing, so to say, so that you have, for example, that you can quantize the electromagnetic field. This is a lot of jargon, but it says that basically the same thing which you do in the case of Bohr's like atomic structure, you do that same process of quantization with entire fields, basically. In this case, the electromagnetic field. So you give the electromagnetic field itself these finite, you could say, values that it can pertain, so to say. So if you typically visualize an electron, for example, as this blurry smear of probability, so imagine then instead of the just electron having this blurry probability smear, imagine then if you have an electron and this electric field lines kind of going into it, that the field lines themselves are also kind of in this weird superposition type of state. So if you have that, which is what quantum electrodynamics actually stands for, classically when you compute it, you get energy differences such as what, for example, Lamb shift found, but theoretically that seemed to blow up to infinity, and this seemed to be a very prevalent problem. So Kramer's solution to this was looking at a Hamiltonian, which describes the total energy of the system, and tweaking it ever so slightly, such that the Hamiltonian had something called the expected mass of the electron and the actual mass of the electron. And it sounds like those two should be the same thing, but according to Kramer's theory, they're not quite the same thing. The expected mass is the experimentally measured mass of something like the electron, but what it actually stands for, if you do Schwinger's formulation, is it consists out of the actual mass of the electron, which is something which is inherent to the electron. It is more or less like its rest mass, so to say, if you were to think about it in terms of like Einstein's theory of E equals mc squared. Every type of matter has a rest mass that is basically its mass when it's not moving. So the rest mass of the electron would be the actual mass, and the extra term basically, which would overall sum to be the measured mass, is something called the electromagnetic mass. It is an additional term basically which you give to the rest mass of the electron due to the presence of this electromagnetic field, which is quantized. That gives you the expected mass basically that you measure in experiments. So it is how much basically the electromagnetic field kind of tugs on this particle and kind of adds to the mass at which you'd measure experimentally from it, which is a very odd thing to imagine, but is actually a very important concept in the overarching structure of things like quantum field theory. So this has to do basically with something called the self-energy of the electron. To do the calculation for the self-energy of the electron, Kramer goes by this very interesting approach that says that when you have the Hamiltonian that tells you something about the particle, you can do something at which the rest mass of the electron becomes irrelevant, such that you're only working with the expected mass of the thing. So you're kind of hiding the actual mass and the electromagnetic mass somewhere in there, at which when you do things with this Hamiltonian, what comes out are things which only depend on the measurement, the expected mass basically. This is a very important way of thinking, and especially when doing field theory work. So this kind of laid the bedrock for, again, Weizsäcker and also a little bit Hans Bethe. So the latter presentation was given by Weizsäcker, who built upon the suggestion of Oppenheimer from the first day, mentioning that if this lamp shift, which was talked about on the first day, indeed was a phenomenon which was related to this quantum electrodynamic effect, then it could in principle be tested for to see whether or not it is of quantum electrodynamic origins. And also further theoretical predictions can also be made of this delta E by using a whole theoretic approach, so to say. This whole theoretic approach is a jargon way of saying that Paul Dirac, when he came with his famous Dirac equation, which was a way already at which quantum mechanics was connected with Einstein's theory of special relativity, so things moving close to the speed of light. Out of the Dirac equation came both the notion that particles have spin, so this intrinsic property of theirs, that they can be spin up or spin down, and they can also have their own antimatter constituent. Actually, they must have their antimatter constituent. It is a property of some of the mathematical nuances called symmetries at which this Dirac equation has. Now, the thing that is tricky about the Dirac equation is that it alludes to there being this negative solution to it, same as if you were solving the quadratic equation for something and you get, oh, x is equal to plus something something, or x is equal to minus something something something. You get the same thing for the Dirac equation, but you get it for the probability distribution of a given particle. So you have a positive probability distribution for the electron, and you have a negative probability distribution for the electron, which sounds very problematic. And theoreticians work this way, and also experimentally it was found to be the antimatter, which is the exact same thing a lot of times as regular matter, but just changing in its charge basically. So for example, if you have an electron, then its antimatter constituent would be an anti-electron or a positron. So same mass, same spin shenanigans, but the only thing that differs is its charge. It would have a plus charge. Now, to explain how you get that the universe must be so nicely symmetric that every particle must have its antiparticle pair. Dirac had this theory called the Dirac C, which is a very elegant but at the same time not quite right theory, they found out later. That is, that you can have a C of negative probabilistic particle distributions, which is a very abstract thing. It is not a real sea in the sense of like an ocean or something. It is more of an abstract thing, like you would think of a magnetic field, which is not something that you see, but you can see its influence of. And the idea behind this C is that when you have a particle popping into existence, like an electron, for example, it leaves a hole in this Dirac C, which is positively charged. Very, 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 like, I'm abbreviating and making a very, very simplified statement of this, as it's much more nuanced and complicated, but that's the picture that you could have in mind. It's like if you read or done some work in electronics, you can have a semiconductor at which you have this material which can conduct electricity in principle as long as you provide it with a little bit of a nudge. If you provide it with a little bit of a nudge, then an electron goes from one atom to the other, like it jumps over, it conducts. But as it does so, it leaves a region that is positively charged because now it lacks an electron. This is the same idea that you can have, but this time with the electron leaving this Dirac C, and that positive charge in this case isn't a lack of the electron, but it is a particle in it of itself. So using this approach, even though people already had their suspicions back then that the Dirac C theory is not the way to go, you can still use this mathematical formalism to make certain calculations regarding quantum field theory. Weizsäcker's idea was that you can make predictions of the energy differences you should get with things like the lamp shift by utilizing this whole theoretic approach. So that is a very long tangent for you to understand that very small little thing which Weizsäcker needed to talk about. But now we go on to the last day finally, at which I found to be the most like interesting conclusions of everything, and that is in the morning you had Oppenheimer talking about what he called the paradox of this meson problem. Like, why is it that we have so many mesons being produced in high altitudes but not in low altitudes? He had a particular theory about it, but Weizsäcker had a much stronger intuition about it, because if they were to build upon the theory which was causing this whole dilemma to begin with, which I noticed, which I haven't talked about, so a small detour. In the past, there was a theory established that the strong nuclear force, so the force that keeps protons binded so tightly with other protons or with neutrons, is mediated through this very small particle called the meson. And basically, this was a theory which Yukawa postulated to explain how protons, especially protons with protons, could be so tightly bound together without them flying immediately rapidly apart, because they're both positively charged and very, very close within nuclear structures of atoms. They're very, very close at distances of like 3 femtometers or something ridiculous like that, and they're not being immediately repelled by the strong Coulombic repulsion which they should be experiencing. The explanation that Yukawa posited was that at such smaller distances, you have that one other force overtakes basically this Coulombic repulsion, and that would be the strong force. And the strong force would be mediated by a particle called the meson, or the pi meson actually, and it would be mediated by such short distances. You should not observe this pi meson in large quantities over larger distances, because it should decay really, really fast, because it can only exist for very, very short distances, having to do with Heisenberg's uncertainty principle. But again, I won't discuss that, otherwise this will turn even longer. But you just have to go with me on that one. So if you have this going on right here, then how, for one, are they seeing such huge productions of the meson, and how is it that they see much less production of it at sea level? So Weizsäcker's idea was that this meson, which again back then they were calling it the mesotron. This mesotron was coming in from outer space, and it might have actually interacted with nuclei in the atmosphere, so for example of carbon, nitrogen, and things like that. And as it interacted with the nuclei in the atmosphere, it brought nucleons, or a nucleon, like a particular nucleon inside of the nucleus in the atom, in the atmosphere. it might have excited it, so produced something that is known as a resonance structure. So just the nucleus being in an excited state. And as it went out of this excited state, it produced another meson, basically. So it would be like this shower reaction, so to say, at which you'd have much smaller or less massive mesons, basically, at sea level. I say meson because this led to the physicist Marshak's very famous two meson hypothesis, at which you have that the pi meson is what's being captured in the atmosphere. There were nuances with that because, well, yes, the pi meson is strongly interacting, but the mu meson is not strongly interacting, and that's why you can have it at much smaller quantities at sea levels because much less of it is being captured by nuclei before decaying. This has to do with weak interactions and the weak force, basically. And that's a whole other discussion in and of itself, which again, back then they didn't know much about. Like the weak force was another mystery of nature, so to say. So we'll keep it at that ourselves, as basically this further working out of this two meson theory was done after this Shelter Island conference. But then the last presentation, which was also given, was by Richard Feynman, and that was on basically his space-time approach to quantum mechanics. And basically, it was his introduction to the Feynman diagrams. Basically, it was how he started to introduce this notion of using Feynman diagrams, which you might have seen all over the place, which looks like these squiggly line things, to describe basically various you could say fundamental particle interactions in a very pictorial way, which is really cool. It basically captures the entire bulk of perturbation theory in quantum mechanics in a more schematic and pictorial way. So that was in a nutshell the structure and what was being discussed throughout this Shelter Island presentation. It's a lengthier video than I expected. So there were spin-offs and very important work basically which emerged from the Shelter Island conference, so to say. So for one was Beta insight basically that this Beta and Weisskopf, both of them, but especially Beta, continued to working and actually do the calculation that this lamp shift could indeed be explained by quantum electrodynamic effects. He did the calculations and found values which aligned very nicely with the experiment. But not only that, he also noticed that in Kramer's theory, which one important aspect of it is that one needs to look at the expected or experimental mass that is being measured by things like by the electron, for example, rather than trying to use that rest electron mass, so to say. That insight is important, but he noticed also that Kramer's theory was classical. It was non-relativistic. So there needed to be a relativistic version of quantum electrodynamics in principle. So he pointed Richard Feynman in this direction, and Richard Feynman, who had already done some very interesting work on electrodynamics, being like a force at a distance type of thing, and also he especially worked during his PhD on this path integral approach of quantum mechanics. So he reformulated the whole framework of quantum mechanics in his PhD thesis, which is kind of nutty to think about. It, of course, inspired Feynman to work on this interesting problem of making QED relativistic, which eventually led to him winning the Nobel Prize right along Julian Schwinger and Tomonaga as well. So that, in a brief nutshell, concludes all that I wanted to say with the Shelter Island Conference thing. It is very interesting, but not as well known as the Solvay Conference because I think the work is clearly more abstract. Like it is not as accessible, I think, as the bedrock foundations of quantum mechanics. That I think tends to be at least communicated in a much more accessible manner to the public. This is captivating, but I feel like for people who already know a little bit more physics. So I hope you enjoyed it, and I hope even if you're not one of those people who are diehard into physics, that this still made quite a little bit of sense. And also thank you for sticking with me for such a lengthy video. I hope that this also, if for some reason you're someone who's watching the road to quantum field theory, that this serves as like an historical tie-in into the theory, because all of this history also makes it a bit clearer as to what the train of thought is when moving through a lot of the technical, like you could say, hard work and jargon. So all in all, hope you guys enjoyed this. Hope you're having a great start of the new year that is about to come or that already started. And hope to see you guys very soon for more content. Bye bye. And also, highly recommend this particular book if you're interested in the history of quantum electrodynamics or just quantum field theory in general. So, yes. See you guys soon and bye.